Welcome to the Explainer. You know, there's this existential anxiety keeping AI developers up at night right now. We're talking about the rapid, honestly breathtaking advancements in foundation models. Will they completely erase years of hard work and multi-agent engineering? Picture this. A startup spends years meticulously designing workflows, specialized tools, and memory systems for their agents. And then boom, a new foundation model drops. It naturally reasons better. It uses tools reliably. It follows massively long instructions flawlessly. Suddenly, it's doing tasks all by itself that previously required a whole elaborate system of agents. So, does that make all that engineering completely obsolete? Well, let's unpack the realities of AI architecture and find out, sticking strictly to the text of our source material today.
Okay, let's dive into this. Here is the blueprint for our rigorous systems engineering teardown of AI architectures. We're going to start with the foundation model threat, move into shallow moats and patches, and then look at the architecture of coordination. From there, we'll break down allocation, memory, and verification, contrast orchestration with system governance, and finally outline building a durable moat.
Section 1. The foundation model threat, when new intelligence arrives.
This is exactly the scenario developers are sweating over right now. It brings us to a massive, really industry-defining question. Will stronger models eventually make the entire architecture unnecessary? I mean, think about it. What looked like a highly valuable, totally defensible product yesterday might just start looking like a temporary layer built around an older AI model's weakness today. If your entire business model relies on compensating for an AI's limitations, what happens when those limitations just disappear?
Section 2. Shallow moats and patches. Vulnerability to model progress.
Let's say your workflow divides a single task among several agents, but it only does that because an older model literally couldn't handle a long prompt. Or maybe you've got an agent whose entire existence is just fixing formatting mistakes, or one that repeats reasoning because the base model was a bit flaky. Look, when a stronger foundation model enters the center of your architecture, it absorbs and just completely eliminates these shallow patches. Why? Because these layers weren't actually creating a new capability. They were just patching a temporary limitation, and that kind of engineering is incredibly vulnerable to model progress.
Section 3. The architecture of coordination. Defensibility through structure.
Now here's where we shift our focus to the durable layer of a system. The parts that remain absolutely necessary no matter how ridiculously smart the foundation model gets. Look, even a highly capable model still has limited time, a limited context window, limited attention, and limited access to resources. It still needs a way to divide a massive project into separate work streams. We're talking persistent memory, independent verification, tool governance, accountability. These aren't simply weaknesses of a specific model. No, these are structural properties of complex work. They are fundamentally irreplaceable.
Our source material offers this brilliant analogy to really anchor the concept. A brilliant scientist does not eliminate the need for laboratories, peer review, project management, records, replication, or specialized teams, right? It's like how a brilliant judge doesn't eliminate the need for courts, procedures, evidence rules, and appeals. Higher individual intelligence changes how these systems are designed, absolutely, but it definitely does not make the need for coordination disappear.
Now, what's really interesting here is that a company doesn't magically become defensible just because it can launch 100 agents. Actually, scratch that. Sometimes throwing more agents at a problem can create duplication, massive disagreements, cascading errors, and crazy communication costs. A massive swarm might look super sophisticated in a demo, while actually producing way less reliable work than just one carefully controlled model. The real moat relies on optimized information flow, conflict resolution, assigned responsibility, and structure decomposition.
Section 4. Allocation, memory, and verification. Solving persistent problems.
The source introduces this fascinating concept called the energetic paradigm. It's basically a framework that views a multi-agent system strictly as a resource allocation and control structure. Think about it. Every single agent you run eats up computation, context, time, tool access, and verification capacity. The system has to decide exactly where those resources produce the greatest value. You shouldn't use 5 agents when one gets the job done. You shouldn't distribute work just to look parallel. It's all about controlled, purposeful allocation.
Then there's verification. You might be thinking, well, a model can just check its own work, right? But a second pass by the exact same model might just reproduce the exact same assumptions as the first. A separate verifier helps, sure, but simply creating another agent isn't enough either.
If both the solving agent and the verifying agent use the same model, rely on the same sources, and optimize the same metric, they literally share the exact same blind spots. True verification requires functional independence. The verifier needs different objectives, different evidence, different tools, and different thresholds for accepting a conclusion. It has to actively search for conditions under which the answer fails. Now that is architecture.
And the exact same architectural need applies to memory. Even as AI context windows expand, real-world projects are always going to exceed them. Long-running work requires an external state. The architecture has to preserve decisions, assumptions, failed attempts, unresolved questions, and the causal history. Plus, a memory system has to decide what not to retain. If you store everything, you just create noise. But if you compress too aggressively, you destroy the history of why a decision was actually made. That problem doesn't just vanish simply because the underlying model gets smarter.
Section 5. Orchestration versus system governance, moving beyond agent chatter.
And this brilliantly illustrates a really critical distinction. First, we have orchestration. This is highly visible. It determines which agent does what, showing them debating, delegating, exchanging messages, the flashy stuff. But then we have governance. Governance determines system permissions. It dictates who can approve an irreversible action, what evidence is required, and how accountability is maintained when things go horribly wrong. As foundation models get smarter, simple orchestration actually gets easier. But greater capability increases the consequences of failure, which means the need for rigorous governance increases drastically.
Section 6. Building a durable moat, absorbing stronger models.
Let's move on and see how this all builds a really resilient strategy. A rigid multi-agent system can definitely become obsolete, so the moat has to be adaptive. When a new, stronger foundation model drops, a durable system follows these steps. It removes unnecessary layers. It gives agents broader responsibility. It redesigns verification around the model's new failure modes, and it reallocates resources toward unsolved problems. You see, a durable system becomes simpler and more powerful by absorbing stronger models, rather than trying to compete with them. If your company only benefits when models remain weak, well, you don't really have a strong moat.
Another massive layer of durability comes from deep domain integration. Whether we're talking medicine, law, finance, or scientific research, useful agent systems must connect general intelligence to specific institutions. They've got to understand domain standards, work with highly specialized data, respect existing approval structures, and produce evidence in forms that human experts can actually inspect. A new foundation model might improve raw reasoning for sure, but it does not automatically acquire these institutional relationships or trust. The deeper the integration between the AI system and the real workflow, the harder it becomes to replace it with just a generic model. Which brings us to our final takeaway, and a really crucial question for you to consider. Can one model, no matter how incredibly intelligent, replace the structures required to turn intelligence into stable, accountable, long-horizon action? Well, the answer we've uncovered today is a definitive no. The real moat isn't about launching a massive quantity of chattering agents. The real moat is the system that converts raw intelligence into structured, accountable action through durable memory, independent verification, and strict governance. So think about the workflows you rely on today. Are they vulnerable patches, or are they built on a durable architecture of coordination? Thank you so much for joining me for this explainer. I hope this helps you focus your learning and see the real structures hiding right behind the AI hype.